I was interested at the time. The robotics was addressing industrial problems like assembling things, and there was
Right.
good results that sort of showed that if you could control the compliant properties or the stiffness of the motion of the robot, it could assemble things better. So I set out to build a hand that would be a programmable, compliant device to help robots put things together.
Cures, Remedies, and Beyond podcast with Dr. Irina, a Stanford-trained medical doctor, inventor, and a published author with over 30 years of clinical experience, is bringing together the science of medicine and the art of healing for ultimate vitality and health. It engages in discussions with healthcare providers, wellness experts, innovators, philosophers, spiritual and industry leaders, as well as health and wisdom seekers to provide you, the listeners, with practical tips and knowledge to help optimize your health and well-being. The Cures, Remedies, and Beyond podcast with Dr. Irina.
Welcome to another episode of Cures, Remedies, and Beyond. Today, we're joined by a true luminary in the field of robotics, artificial intelligence, and cutting-edge healthcare. Our esteemed guest, Professor Kenneth Salisbury, is a prominent figure at Stanford University, where he leads the Stanford Robotics and AI Lab. Ken is a visionary whose profound academic impact made a big mark on the future of medical technology, redefining the possibilities within surgery and medical interventions. He published over 250 scientific papers and has more than 50 patents. He also received several most prestigious national and international awards in the field of robotics and AI. Ken contributed to the development of telerobotic systems aimed at enhancing dexterity in the operating room settings, like with the famous Vinci surgical robot, and he's a founder of Salisbury Robotics Company. And currently, his research focuses on the intricate dance between humans and machines, exploring areas such as cooperative haptics, medical robotics, and surgical simulation. Ken's commitment to advancing the field has opened new frontiers in understanding how technology can be harnessed to improve patient outcomes and elevate the capabilities of medical professionals and also enhance their training. It is such a privilege to have you on our show today, Professor.
Thank you, Irina. It's great to be here, and thank you for inviting me. I appreciate it.
So you had designed and built a robot hand for your PhD project in mechanical engineering at Stanford 40 years ago in 1982. Wow. Yeah, I didn't know about that. So my first question is, how did you get interested in robotic hand that you're so famous for in the world?
Well, one quick comment about the date. The computer we used to control that hand was called a VAX, V-A-X, and it was about the size of a washing machine. And I think most of it was cooling fans, but it was now my cell phone probably could do the whole job. I don't know. There's an artist in me that always wanted to make sculptures, and I got interested in kinetic sculptures. So I'd go to flea markets and buy motors and solder things together. And we're talking before high school, and I've always been interested in hands. I have found at my family home, fingers that I've made, just little joints that I was playing with, just trying to understand, what could I do? What could I make? But actually, I think I was in high school and my father had a stroke, and I used to go to physical therapy with him. As much for emotional support as anything. But I was really fascinated with the therapist working with him, trying to help him, regain some use of his hands. Mm-hmm. Yeah. And I actually built some rubber band gadgets to help him exercise at home. And I considered becoming a physical therapist at one point, because there's, some knowledge of mechanics, biomechanics, but also the psychological component of, helping people work to get better. But I got seduced by the dark side and ended up in a robotic lab making robot gadgets, and I mean that kindly. But I'd always been interested in. I could see that computer control of mechanisms was going to come, electromechanical systems or mechatronic systems, as we call it today. So my studies were in electrical and mechanical engineering, and I was interested at the time. The robotics was addressing industrial problems like assembling things, and there was
Right.
good results that sort of showed that if you could control the compliant properties or the stiffness of the motion of the robot, it could assemble things better. So I set out to build a hand that would be a programmable, compliant device to help help robots put things together. And so the funny thing is that my hand, which is a 3-finger hand, was really just designed for tip prehension, holding things in the fingertips so that it could maneuver them around. The big problem generally with robotic hands is how do they grasp things? Cylindrical grasp, spherical grasp, pinch grasp, and all that. I didn't even think about that part. I was more interested in making it move. And that was a kinetic sculpture in a sense, but it actually had a purpose.
Wow. How was your robotic hand different, like being different from others? I believe that you did something more unique.
Yeah, well, I focused very much on the ability to control forces. So, we do this unconsciously. We control how hard we push or twist or pry or probe things because we need to have control over the forces in order to accomplish tasks. So the hand had force sensors, had tendons because the motors were so big they couldn't be in the hand for sure. And the tendons had sensors near the base of the fingers so that you could measure the tension in the tendons. And so then you could control the motor motions in order to get the desired force. So if you wanted it to pinch, you turn on the motors to a certain point until you sense enough force is being transmitted to the fingers to get your grasp.
That's amazing. I saw a picture of it. It looked like a huge caterpillar with the with this beautiful dexterity. I mean, it's just so unique to me to understand. I mean, we take our sensors sometimes for granted, and we don't even realize what a huge complexity, not only the simple, as you said, grasping that is so different depending on the size, the shape, the texture of the object, can vary but also, the coordination, so, and of course we have a brain, but robots obviously have certain, type of brain, I suppose, not as advanced yet. So,
one of the problems in robotics is explaining to a robot how to do something. And that problem keeps coming back again and again, and we'll get to more of that later. But part of my work with my hand for my thesis work was to come up with a way to describe how to move the fingers and how they should move when forces were exerted on them. So I kind of encoded some behaviors in a way that became fairly standard for this kind of in-hand manipulation.
Right. And you've been also like one of the pioneers in the field of haptics, within the computers. Can you explain us what's the difference between haptics and robotics?
Yeah, well, more and more they're related, and in my own research, the two fields are coming together. So haptics has been around forever. It comes from the Greek meaning to touch or to take, and for a long time, people studied human haptics, our ability to perceive forces or contact or motion of objects on the hand. So there's sort of the human haptics field that came before robotic haptics or virtual haptics. The kind of haptics that I've gotten involved in, one of them is virtualized haptics. So if you want to enable somebody in a virtual environment to feel something, how do you do that? Well, you make a little robot. Actually, I have one sitting on the table.
Yeah, can you show us?
Okay.
That is exciting.
So this is one of the original phantom haptic interfaces, and we designed this at MIT in mid 80s or late 80s. And so it has motors on it. The things that are moving are motors. We have 3 motors. So I can move the tip of this thing in X and Y and Z by turning on the motors in different ways. And so if I attach a stylus to this, I'm going to put it down now, I can maneuver that stylus or handle as though it were an instrument, and it could be configured to feel like I'm carving clay, or I'm drilling bone, or sculpting some virtual material. And so those motors would turn on just at the right time and in the right way to exert forces back on my hand. So that's a way of doing virtual reality where you can actually feel the forces. In VR, there's a lot of interest in vibration to give you cues and illusions, which is okay. That's scalar information. It's sort of simpler information than the force vector information you get when you have 3 or more motors pushing back. So you can actually feel the solidity of things, not just vibration in free space.
Right. Well, and I mean, I guess for also our listeners to understand that, it is so important what you're doing, obviously, because the safety actually of the robots hugely rely on this, senses. So.
Yeah, well, a mirror image of the kind of human haptics is robot haptics. And so if a robot's working near me, or maybe it's even a medical robot that's helping stabilize because I have a broken bone or stop bleeding, it needs to have a haptic sense of its own, so that if I tell it to push lightly or push firmly, or don't move, don't let me move, or help me move, it has to be able to sense and control those forces. And I think I mentioned to you the other day, I'm starting a new project to develop a remote emergency medical technician. What does that mean? And that's a 10-year project that it's public, that Honda Robotics is working on. And I said, first year, all we're going to do is work on enabling a robot to touch a human safely, predictably, knowingly, so that when it touches, it can tell if it's touching a rigid part of the body or maybe a compliant part of the body. So that there are multiple versions of haptics, whether you're trying to simulate building or working with something in VR, or whether the robot is physically interacting with me to do physical therapy or triage, or who knows what.
Right. Wow, that is interesting. So also that I found out reading about you that you actually move at some point onto intuitive surgical. So where you were basically working on the enhancement of the surgeons' skills with robots, and developing that famous Da Vinci surgical robot. So can you tell us more about that?
Yeah,
because that is the most amazing breakthrough, obviously, in the robotics in the surgical field. So that now surgeons obviously can operate in a completely different state, obviously, so using this system.
Yeah, no, it's a good story, and it was sort of crazy when I first heard, like, we're going to make a robot to help surgeons do surgery, and it's like, yeah, but actually it's
reality now.
it's quite real. At the time I was at MIT. I went there after I finished my degree at Stanford, and had been working on telerobotic or remote manipulation systems. And let me define that, because it comes back. So early on in my education, I met a fellow in France named Jean Vertu, who designed remote manipulation systems for servicing nuclear reactors. And so this goes back to the 40s. This is called teleoperation or remote manipulation. And in his work, he would have a controller that the human in a safe part of the world environment would be controlling a robot-like arm working inside the contaminated area, whether it's servicing the reactor or working with hazardous materials. And I learned from him quite a bit about force interaction and the ergonomics. If you're trying to transport your physical capability to another location, what are the characteristics? How stiff does the system have to be? How massive can it be before it's inappropriate? And how sensitive must it be in its range of forces that it can control? So that took me to it was great lessons came from Jean. He really had a profound influence on me. Among them, that I'm known to be obsessive about using cables in my robotic things, and that's his fault or his gift in some sense.
That's interesting. Well, we all have cables that we call tendons, ligaments, right?
Totally, yeah. And there are remarkable one of the several exciting things happening in robotics is that there are remarkable new tendon materials coming, synthetics that are way better than steel cable, that are strong and durable. It's all the things that I wanted 40 years ago. I can get them now. So my second experience in telemanipulation or telerobotics was a NASA project where they wanted to design a controller for controlling the space shuttle manipulator. So an astronaut in a pressurized environment is, using this fancy joystick to control the shuttle manipulator to grab a satellite or do some servicing. And so,
wow, interesting. That was would be outside, of course, of the actual station, right? So
yeah, again, with the purpose of transporting the human's skill and dexterity up to a hazardous environment, vacuum in this case. We never flew the device that I built, but I can show you a picture of it. Can I move my camera here?
Yes, please. Oh, that's really remarkable. Oh, wow.
So it's kind of like a giant joystick, and it has motors at the back end, and then it has mechanism, and it can telescope out.
Interesting. Is that a vacuum tube that you have there?
No, it's just see-through so we could see the mechanism.
Oh, I see. Uh-huh.
So the purpose of this handle was that the user would hold the handle and control the remote manipulator. And
wow.
Go back to...
Wow, that is impressive because, of course, for NASA astronauts to have the, extra vehicle experience, so, it takes unbelievable amount of resources and hours to train them. So, and of course, a lot of risk involved to be outside of the craft. So, and here you actually were trying to help them to create something.
Yeah,
a robotic arm, so that they would be still sitting inside of the capsule. Wow, that's impressive.
That work preceded the Phantom, the black haptic interface that I showed you, but it kind of informed some of the answers. Gave me some of the answers and raised new questions that evolved. So roll forward a bunch of years, and I'm at MIT, and I'm working with a student whose father was a surgeon, and he wanted to make a remote surgical system, and he wanted to tie knots with it. This is with Akhil Madani, and so he developed a robot. I think it was called the Silver Falcon or the Black Falcon, which was very much like the Da Vinci robot. So he and I are working our way on this. Didn't know anything about intuitive surgical, and I got a call from their CTO, Chief Technical Officer, who was from my freshman dorm. You remember your dorm mates because they come back in your life sometimes. Wow, yeah. And he said, "We raised $100 million, and we want you to help us build a robotic thing, but I can't tell you what it is yet because I had to sign, non-disclosure." Well, fast forward, it turned out we were working on the exact same thing, and he invited me to leave MIT and come and be the scientific advisor at Intuitive Surgical.
Wow!
So, lots of interesting problems. My student Akhil Madani came and worked with Intuitive, and others since then have gone there. But the most interesting problem that I solved there was the handle or the haptic interface that the surgeon holds on to.
The next demonstration is of whole hand control of the stiffness. We've asked the hand to be compliant for motions in this direction. As you can see, the fingers move together. For motion in all other directions, it's relatively stiff. So that if the hand is holding an object, that object is compliant along that axis of motion. However, it's relatively stiff for motions in all other directions. Again, this would be useful in trying to assemble objects in constrained situations where you didn't want to exert excessive contact forces.
So, and they brought a few of those robots actually to the conference. So I did try, and I actually was able to use it myself. So to cut, so the bone, so to speak, of course, the fake bone. So, and it was more, well, first of all, it was more difficult than I expected. So, and they also said that we're not there yet to, of course, have it completely independent from the surgeon. So, but what they described is that it greatly improved the precise incision over the bone. So, because that, of course, determines, how well the prosthetic part will sit on the bone, so that the leg will not be curved, so after the surgery, any, particular direction, right? So, and just to the millimeter, so the software, which is of course AI behind, the actual physical part of the robot, so was also calculating using either the CT scan evaluation, so or some other, three-dimensional evaluations of the parameters, so at what level we need to, cut off, part of the bone, for example, so that the prosthesis, will be perfect and exactly replicate the length and the angulations of the other limb, for example, right? So in case of the either hip or knee replacement. So but but of course, they also, what you just mentioned, they pointed out that we're definitely not at this stage aiming for the remote operation. I mean, not aiming for the surgeon to being in the remote location. So, but rather inside the surgical room. So, and still be hands-on. So just kind of have this as an assistant, as an amazing assistant. So at this stage, because I thought that initially, so the goal of these robots for surgeries were, to deliver specific better care for, patients that, for example, don't have an access to really, well-trained surgeons, and then they live in some rural areas. So this way, of course, they have this access to the, academic teaching institutions that, those surgeons perform these unique surgeries, so on patients that live somewhere in very, very rural areas that have no other option. So, but it doesn't look like we're quite there yet. So my understanding.
Yeah, telemedicine is good for diagnostics and communication, but physical tele is over distances and dexterity at that level. That's still pretty hard. I'm curious, was it the Mako surgical robot you were looking at?
They actually had 3 different companies, so they all have the different kind of software-based approach. So some actually with the use of CT scan films prior to, some or during the surgery, some are actually even without, that have a very compact systems, so and the advancements are incredible. So I have to say in that field. So, but I was really surprised to see that, I'm obviously in the San Francisco Bay Area. So to see that UCSF and Stanford, they do actively train their surgical orthopedic residents in the robotics now. So it is definitely going to be a future of medicine. So we're not going to obviously, now revert back. So the train left the station, I have to say, and you obviously have like an incredible contribution to that field. So we're going to take a quick break. So, and we will be right back with our amazing Dr. Kenneth Salisbury.
This podcast represents the personal views and opinions of the host and the guests and does not constitute medical advice. The statements contained in this podcast have not been evaluated by the FDA. Any products or treatments mentioned are not intended to diagnose, treat, or prevent any disease. And now your host, Dr. Irina.
So, Ken, could you please share with us more on, what are your other favorite inventions that you have created so far, or medical projects?
Yeah. Well, the haptic interface I showed you is one of them because it was so simple. I worked with a student, Thomas Massey, who's now in the U.S. Congress. He's bubbled up to a new position.
Wow.
Yeah, he's quite the guy.
We need doctors there, right?
Yeah. Well, he even says we need more doctors and engineers and scientists in Congress so they can make rational decisions. We'll see what rational turns out to be or not.
and have some, trained critical, thinking abilities, not just emotional and whatever, so financial. Yeah.
Well, there's another medical robot that you reminded me of. there was an arm designed by Bill Townsend called the WAM arm, whole arm manipulation. And it was kind of a big haptic device, but it was designed for very good force control. Just the mechanics of it were, specially made so that it was good at exerting carefully controlled forces. So that was licensed by a company called Mako Surgical, and it was used in the same context I think you were just describing, where the surgeon we're doing knee surgery in this application, and you need to cut a space where you can put in a prosthetic, a bearing surface to replace a worn bone. So you need to cut a very carefully shaped pocket in the head of the bone. So the surgeon would have the cutting tool, but the robot would also be holding it, and it would be constraining the surgeon to make the cut in just the exact location and of size and depth and orientation needed. So
yes,
and that turned out to be a huge success in improving the outcomes.
wow.
So that same technology, it's now called Barrett Medical, has become a stroke rehabilitation robot. So its ability, it's called BERT, B-U-R-T, and the company is Barrett Medical. And the reason, again, this whole force control scheme, which goes back to Jean Vertu, it's a cable-controlled arm. But when you're doing patterning or whatever else you're doing, therapeutic action with a stroke victim, you need to support their arm, and you need to maybe provide some assistance. So this is going back to my interest in physical therapy. So the same technology that was good at putting pegs in holes, that made an interesting hand, rolls forward to this arm that is now helping stroke rehabilitation for upper limb rehab. So it's just sort of one of the. I did it because I thought the technology needed to be developed, and then we keep finding, well, actually, it's useful in here, and it's useful over here too, and it's kind of been a happy theme in my life that I like to invent things that are maybe different and have higher performance or different kinds of behaviors than had been seen before, and then you discover, oh, actually, I can do something useful with this.
Yeah, no, that's amazing. And then also, I mean, if you could tell us about Toyota's recent announcement and why you're so excited about it, because I know you work for the Toyota robot development as well.
Yeah. Well, the Toyota Research Institute, which has grown over the last 8-10 years, about 400 people. They have centers here in Los Altos, but also around the country. They've been, as have many people in robotics, very interested in how do you train a robot to do something? How do you demonstrate, rather than writing line after line of code of move here until you feel this and then go left, blah, blah, which I've done and I don't want to do again. How do we teach a robot to do something? And in the machine learning world, there's been a lot of work using visual examples to teach the robot or to do machine learning. So have the system look at a million examples of people putting something in a drawer, and you can extract from that a strategy and a behavior where you can now tell a different robot, take that bag of potato chips and put it in the drawer. And from what it's seen on those many cases, it can infer how to behave. But the problem so far has been that what I just described doesn't measure the forces of interaction. So if the drawer is stuck or has a fork in the way and you need to move things around, or anything that has any kind of physical information, is not really been attended to. So the folks at Toyota did teleoperation. They had some haptic controllers that the human would hold on to, and they would be doing remote manipulation of simple tasks, kitchen tasks, cutting things, spreading things, opening things. And what's different in their experiments is that they observed the forces of interaction, just as one would want to do if you're servicing a nuclear power plant or doing surgery or repairing a satellite. So lo and behold, if you observe that much faster and much more robustly, how to do the task on its own. So this was a press release from Toyota, Toyota Robotics Institute, September 19th. So read about it. It's we've all been excited or frightened both ways about large language models and chatbots. Those deal with information, textual or visual information, but not physical information. How should something feel when I'm putting a lid on it? It gets stuck, or the door is locked or not locked.
Right.
So the new term is large behavior model. So it's behaviors, which encompasses the forces and the motions and the stiffnesses and all the mechanical things that are going on. So this is really exciting. Wow. It means you can just show robots how to do things. You don't have to write code.
Wow, so interesting. And it basically does that self-learning and self-advancement using, of course, the AI. And wow, that's interesting. So it's basically like Chat GPT, for the software, but it's in the physical three-dimensional space.
Mm-hmm.
Plus okay, the software, of course, as well. So, and it's so much harder, obviously. So, I mean, I remember when I was in Japan, 25 plus years ago. So I went to their Museum of Innovation. So, and that was the first time that they actually showed a humanoid robot that was actually able to stand on 2 feet and actually, go up the block, so, and be able to have a coordination without falling down. And it took them so many years and so much effort just to achieve that simple task that we also take for granted, right? So how is it possible to stand, so on 2 feet, so without falling off, so, but for robots, it's extremely difficult. So, and so I can't even imagine how many, seemingly easy tasks that humans are able to do. It's just so difficult to reproduce in a robot, obviously. So, wow.
Well, there's an analogy I like to make, since my skills are mainly in how to design mechanisms that work well. And so if you buy a stereo, but you have lousy speakers, it doesn't matter how good, your source of music is. If you don't have good speakers, you're not going to get the quality of it. So same thing with your robot. If it's kind of clunky and has friction and backlash and all kinds of mechanical badness, that's not going to be very deft or dexterous. Where if you spend the time to make it behave smoothly and with low friction and no backlash and other mechanical things, if you do that right, then you're going to enable the dexterity. You still need the brain. You still need the source of control. And but that's so both sides of the coin are coming along. I'm pretty excited about robotics.
Yeah, it's a good analogy. But also, I know that you actually, and you showed me a few magic tricks that you know how to do, and you also play flute. I was wondering how that is important to you in your work.
Well, let's talk about magic and knot tying first. I'm obsessed with doing things with my hands. I can't juggle. I don't have sort of dynamic skills, but I used to teach knot tying when I worked with scouts, and I have many books about how to tie knots. I just find them fascinating. And the other night I was not able to fall asleep, and I realized I can just imagine tying different knots. So I kind of went through about 10 different knots, and okay, it goes here and it goes here, and so I can almost imagine how it feels. I have a good physical imagination, and when I design things, when you actually make it, it's like, oh yeah, deja vu. This is kind of what I imagined it would feel like. So that's
it's like what athletes do, right? So in a way, right? So to have mental training for the same exact performance, so that enhances it quite significantly.
I also have probably 100 magic books, and I can do a few tricks medium well, but I'm just intrigued with descriptions of how to do things with your hands. So it's, again, we come back to the language problem. How do you explain to another human being who has some context how to make a card disappear or a coin appear? They have some basic knowledge, but then there's still instructions on top of that. So looking at the language that magicians use to describe to each other how to do things has been fascinating. As far as the flute goes, there's always been music in my life. My mom played the piano pretty much nonstop. I inherited her passion, not her skill, but I played the flute for many years, and it's just a comfortable place for me to go. People say music does that for them when you're stuck on a problem or just need to shift gears. Just completely different context. And I like Baroque music. I can improvise to some degree, but I'm not a jazz musician.
Oh wow! Yeah.
You heard. Yeah. It's been a great adventure. This year was I think my 15th year, and my older daughter's 14th year. So we've gone together for many of those years. I was encouraged to go by my thesis advisor, Bernie Roth, who just turned 90 this year, and he came to the burn himself, and he said, "Ken, it will change your life. You got to do it." And I hesitated for a couple of years, but finally did. On the music front, I'm a fairly shy performer. I don't like recitals and that sort of stuff, but I really do like to share my music. So at Burning Man, it's so chill. You just set up your music on the corner and start playing, and people show up and sit down or clap as they're riding their bikes by. So it's very casual. Part of the Burning Man culture is gifting, and that in a way that's one of my gifts is to share some sounds that I like. But for the Burning Man art part, for me, I made an extensive set of playable chimes, like you see in an orchestra bells, and I tuned them very carefully. But part of the art is the process of making it, so I would tune them really, really precisely. And some of them had Western scales, pentatonic scales that sounded good to the Western ear. Then I made an Indonesian set, which was a gamelan tuning, which is 9 or 7 notes per octave, which sounds really strange to the Western ear. But sure enough, a couple of gamelan players showed up at my art and played it, and they were just like totally happy.
Oh, wow.
So I mean, it's a social event. It's there's so many interesting people. My mother was a pyromaniac, and I guess I inherited that too. So I like to I mean that nicely. And so I like to see
special effects.
Yeah.
That's right. Wow, that is really interesting, I have to say. Wow, thank you for sharing that. So, well, and I just wanted to ask you, I mean, where do you think we're going with the robotics, with the AI? I mean, are they going to really replace us, or are they going to be a good assistance? Or, I mean, what do you see? I know there is a lot of course, ethical issues that have to be squared away, and decided upon, so, but aside from that, I mean, like, where do you think we are going in terms of the beautiful technology itself?
I don't know. 40 years ago when I started this robotics thing, I don't know if I could have predicted we'd be doing surgery on, people that I know.
That's right.
I can't really speak to the future of large language models and where that's all going to go, and chatbots and all that stuff. I think it's exciting, and we got to keep a close eye on it. In the physical world, as you kind of picked up, I'm pretty excited about the fact that humans can physically show a robot how to do something, and that it can learn to do it. I mean, it's just intellectually intriguing, but we'd like to get to the point where we can show a robot, this is how you adjust the valve in this power plant, and there are 20 of them down the road. So could you please go and adjust all of those, because it's hot and it's hazardous, and we'd rather have you, robot, doing it. But I need to be able to show you how to do it. So the resources for teaching or demonstrating to robots, it's starting to come along. The mechanics are good. Motors are getting better. Electric cars are helping with batteries and motors and a lot of the components that we need for robotics. Computers keep shrinking and getting faster, so computation is all good. So the resources are there. It behooves us to use them wisely. I'm excited. There's kind of an emerging field called physical human-robot interaction, where the robot is not just there doing things and acknowledging your existence, but it's actually physically doing something with you. And whether it's helping me with construction by helping carrying a load, or whether it's helping me navigate because I have a cognitive or physical disability, there's physical communication that's going on in those things. In those areas, it's haptic communication in a sense. And so enabling machines to do that appropriately and helpfully and reliably and all those things, I think, are challenges ahead and real opportunities.
Yeah, wow, that's beautiful. I mean, I was so surprised actually to learn that what you just mentioned, so that robots, especially in the wellness healthcare field, so now already helping autistic children So, to have a good feedback and, a little bit more training in terms of the social interactions as an assistant to parents, obviously. So, and also for PTSD. So, I mean, there are a lot of interesting projects that have been in the pipeline, so to speak, to help us as assistants in the elderly care. So, and of course, for people who are lonely and isolated. So it's really interesting that a person can interact. So and this little machine will play them their favorite music or even have certain conversations. So based on that particular person's background, so preferences. Yeah. So
I was going to say, I think there's a growth field in designing personalities of robots. If it's a child care robot, it should have one personality, and not just words and emotions, but maybe touch. Or if it's a security robot, that's a different kind of personality. Or if my GPS, maybe it's going to get annoyed at me and say, "I told you to turn left back there." I think there's an opportunity for some fun and creative things to make them engaging.
Right. That's so true. Yeah. So, and I know there are so many people are a little bit concerned, of course, about, robots taking, so many people's jobs away, right? So what we're going to do. And, I mean, it's a valid concern, but, in the idealistic, I guess, world, so my personal opinion about is that, why not to keep developing this unique systems, this unique robots that will take, away, from us certain less skillful work. So, and why not to, allow them to do things that are just, mechanistical, so not necessarily as creative. Why not for us to actually work 4 hours, every day rather than 8 hours a day? So, and then let the robots do the rest for us. So, and then meanwhile, we will be using our own, amazing creativity, so our talents, so and keep developing, human skills, so, and let the robots, swipe the street, so to speak. So.
But there's a medical example of that. I've forgotten the name of the company, but they've developed a robot to provide assistance to nurses. And it's really simple stuff like fetching a bunch of pillows, or, they forgot to bring the food tray out, so go and get the food tray. So the nurse can focus on helping the person with the things where they really need to be thinking, not just moving stuff around.
Right. Highly professional. Yeah. So something that we humans are so good at and probably will never be substituted by robots for. So, but yeah. So anyways, wow, that was a really delightful conversation. Thank you so much, Ken. So it was such a pleasure having you here, and thank you for sharing this amazing landscape, so that probably in a few years will be just a standard of our living. So, I mean, look at ChatGPT, right? So it's just completely swiping the world, right? So, and it's less than a year that it was released to us, and now it's, writing essays in San Jose, so there was a first play actually put on the stage that was written by ChatGPT. So it's really amazing.
Well, this is actually not Ken. I'm actually a chatbot. I'm not a real person. No, I'm kidding. No, I'm really here. I guarantee that.
You are real. You're more than real. So.
Whatever real means in this context. But
That's right. Yeah.
Good.
Well, thanks again. So, and it was really interesting conversation. We appreciate it. So.
My pleasure. It was fun. Thank you, Irina.
Yeah.
And take care.
Yeah. Thank you for joining us at Cures, Remedies, and Beyond, exploring science and the wisdom of health and healing. We hope to see you next time.